Progressively over time, we've learned more and more about what I'll call how rivers behave and the results of this behavior in terms of the landscape of the river valley. The understanding that we have derives from a long historical observation and record. And the reason, of course, for this is that some of what we call the earliest civilizations in the world are all, in fact, ones associated with rivers. Some have called these the hydraulic civilizations. There's a great deal of cumulative knowledge from those experiences, which has been codified in some ways and improved upon, if you will, or extended more recently.
In observation of natural alluvial channels over many years, scientists have developed a series of fundamental principles to describe channels and the processes responsible for their form and behavior. We know that channels and streams exist in nature. They have a form and shape that varies across the landscape. They have characteristics such as pools, riffles, and meanders, which repeat themselves within the channel. Because these channels have formed without human interference, natural streams are considered self-formed. Despite the variable nature of flows, geology, climate, and vegetation, there is a consistency of channel features that repeat themselves given similar conditions. This indicates that common processes are involved in creating and maintaining channels. One of the consistent features of natural channels is the Bankfull stage.
What we now begin to see is that the river and the associated bottomland, we'll call it, that is the area which the river sweeps in one way or another, which consists substantively of the materials deposited by the river, represents a set of adjustments in what we call the alluvial river, as opposed to, let us say, the rock-bound river. An alluvial river, then, is one in which the landscape, the bottomland, the channel itself, are formed by the river itself under conditions of flow that usually vary from very low flows to floods of very high magnitude. What we see in these river valleys is, in fact, a channel that is formed over time by a mixture of high and low flows. And these flows carry sediments, particles of various sizes and so on, and they mold, if you will, the channel itself and the bottomland associated with the channel.
Some other commonly accepted generalizations about alluvial channels are that the general form of the channel persists in the current climatic regime. Flows reaching or exceeding Bankfull stage are attained with moderate frequency, usually every year or two on average. Bankfull flow is a surrogate for the full range of flows that form the channel. Bankfull flow completely fills the principal channel to the elevation of the floodplain.
The Bankfull then is a surrogate, in a sense, for the whole range of flows which make up the channel, but proves to be a value that can be useful in talking about the behavior of the stream channel and, in part, the range of flows that matter in sediment transport.
Information about Bankfull dimensions is useful for channel restoration, especially in applying concepts of natural channel design. Information about Bankfull discharge in the Bankfull stage is also an important component of river surveys, inventories, and river and stream monitoring. Many protocols rely in part on some aspect of Bankfull stage and discharge identification. In all cases, correct and consistent field technique is essential in providing scientifically defensible information. In this program, we'll discuss various aspects of Bankfull determination. We'll define Bankfull stage and discuss the importance of Bankfull discharge. We'll demonstrate how to consistently estimate or identify Bankfull levels for a variety of stream types typically found in forested areas in the eastern United States, using available data and indicators in the field. finally, we'll describe a consistent, systematic, reproducible procedure for determining and verifying that Bankfull stage has been properly identified. As shown here, our discussion of Bankfull stage in this presentation will focus on forested streams representative of those found in a variety of different regions in the eastern United States.
Bankfull stage is defined as that stage when stream water just begins to overtop the floodplain. The floodplain is defined as a relatively flat depositional surface adjacent to the stream and being built and rebuilt by the stream in the present hydrologic regime. Accordingly, a floodplain along one or both banks is necessary for the determination of Bankfull stage.
Bankfull stage, then, is the stage at which water just begins to flow onto the floodplain. The key to identifying Bankfull level is to identify the floodplain, the flat depositional surface immediately adjacent to the river that is formed and reformed by the river under current hydrologic conditions. Although shown as flat surfaces in this diagram, floodplains and terraces may slope away from the channel slightly and may be traversed by a complex mosaic of remnant features, depressions, or subtle swales of previous channel positions. In many instances, natural levees slightly above the Bankfull stage will border the channel. The important thing to remember is that Bankfull stage occurs when water just begins to overtop the floodplain. The key to identifying Bankfull stage is to locate the relatively flat depositional surface of the floodplain.
The Bankfull stage, of course, represents an integration of a range of flows that carry a range of discharges as well as a range of sediment in transport. And hence, in a way, the Bankfull discharge is a surrogate or substitute for the sequence of flows responsible for the formation of the channel. It can be useful then in that surrogate sense, but it does not physically describe in and by itself the flow that has made the channel, because that is not a constant flow. It is a range of flows from low to high, requiring both deposition in the one instance and erosion at the same time.
Now let's look at data from 4 U.S. Geological Survey hydrologic benchmark station sites and discuss the frequency at which Bankfull flows occur in different regions of the eastern United States. Hydrographs for these sites illustrating unit runoff to the same scale over a single year show seasonal trends that are principally generated both from snowmelt and from rainfall. Peak discharges in any given year in any given location may be greater or lesser than those shown here. On average, Bankfull stage is reached or exceeded in 2 out of every 3 years in most locations. Compared to other regions of the east, runoff in Minnesota tends to be of lower magnitude than moisture areas in the east and south. When Bankfull stage is reached during spring runoff, flows frequently stay above Bankfull for extended periods of time. Occasionally, there may be short periods of above bank flows from rains in the fall. By contrast, in most other streams in the east and south, the timing of flows exceeding Bankfull discharge is very irregular, typically occurring 2 to 3 times a year. Because these flows depend on large storms or saturated soil conditions, they tend to stay above Bankfull for short periods of time. However, the cumulative duration of flows exceeding Bankfull stage in these rain-dominated systems is approximately equal to that from snowmelt regimes and are therefore sufficient to accomplish the work necessary to form and maintain the channel.
Flow in these regimes is driven by rainfall events. Large rainfall events may occur any time during the year. In the snowmelt regime, it occurs only at one particular time of the year, and it is all at one time, whereas there may be successive events bankfull events in a year, the cumulative duration of which may be similar to a snowmelt event, and this supposes that the amount of work being done would be similar in both cases.
Most people take finding the bankfull elevation seriously, and you should too. But to be honest, when you're new at this game, you're probably too conscientious, maybe too picky, too enthusiastic. A lot of people jump right into the channel and start looking for the bankfull elevation. There are just too many opportunities to pick up false indicators when your eyes start down in the channel. Instead, back up and get the bigger picture. We're southwest of Grand Rapids now on the Sugar Hills Moraine, a glacial terminal moraine. And as we look across this valley, we see the high hills on either side of it. These are glacial terraces. And there are several levels, 2, 3, 4, even 5 levels as we go down these hills. But what I want you to see before we get to the stream is the valley flat. That's the elevation where you want to begin looking for the bankfull elevation. When we get down closer, we can look and see if there is a low terrace and, of course, the actively forming floodplain. This area was harvested first in about 1872 when large white pine were removed. At that time, Pokegama Creek behind us in the center of the valley downcut about 1 foot. So let's go down and see if we can find the difference between the low terrace and the floodplain. We're down in the valley of Pokegama Creek, an E5 channel, sandy sediment. I'm standing here on a low terrace, but if you look behind me, you can see the high hill, which is the glacial terrace. About midway down the hill is a mid-terrace. I'm on a low terrace. It's the elevation of the floodplain over 130 years ago. The slackwater channel in front of that terrace is the channel in 1872 when the white pine was cut. And the active channel is about 10 inches lower in the foreground. And you can see where its floodplain is now. So this stream has downcut about 10 inches. But think about the valley that you're in when you're looking at low terraces. For instance, we might be in New Hampshire or Maine on the Whitewater River where sediment is the size of big cobble, like footballs, and the stream may be a river 150 feet across. In a bigger scale situation, the low terrace may be 2, 3, even 4 feet above the current floodplain. Let's take a look at the actively forming floodplain on a little bit of a straight section here and note some features that are very common in the eastern United States. First of all, the channel side itself, when you get close to the top, is actually rounded over, and you have to get up over this round until you get actually to the flat part on top, and that is the bankfull elevation. It should match up with a flat on the other side, unless you have a low terrace there. The other thing I want to point out is that this grass is less than a week old. And in another 2 weeks, this entire feature will be covered with grasses and herbaceous plants. So you have to reach down and feel. A good way to tell that the flat is to look at your foot. If your foot's laying flat, you're up on top of the floodplain. If your foot's still at an angle, you haven't reached it yet. So bring it all the way up until it's flat. Now let's get closer and look at the details of the low terrace and the floodplain. That gray bark birch across the stream is on the low terrace. It's been there for perhaps 100 years. But if we look right where I'm standing at the fresh deposition of this sand on the floodplain, we can see where the floodplain is being built and rebuilt by the action of sediment being tossed out on the floodplain. It's this flat depositional area you want to look for. And remember, in July and August, it'll be covered with grass. But if you put your hand down through that grass, you'll find the sand underneath. Now remember this as you go down valley and the stream meanders from one side to the other, that as you make that journey, the low terrace will alternate from river left to river right, back to river left, back to river right. And the floodplain will be on the opposite side. So be sure and look on both sides to decide where the floodplain's at. Now let's look at one other feature about eastern streams relating to the base of trees. This tree is a good example where the base is well below the floodplain elevation. In the eastern United States, vegetation is not a good indicator of the Bankfull elevation. This tree, for instance, is well below the Bankfull elevation where I'm sitting. Grasses and shrubs will grow below the Bankfull elevation as the growing season progresses. Almost always, trees that are next to the bank, even for large rivers, the side that's next to the bank will almost always be underwater at the Bankfull elevation.
A terrace is an abandoned floodplain unrelated to the current hydrologic regime. The occurrence of several terraces or benches along streams in the east is common. Terraces may be formed by climatic change or by a change in watershed conditions. It's especially important to be able to recognize terraces formed by changes on the watershed. In the east and south, changes responsible for formation of terraces typically include urbanization, logging, and historic agricultural practices. Let's see how these changes on the watershed have historically led to terrace formation. In many parts of the south and east, land was heavily forested in the pre-settlement period. Streams existed in a natural, pristine state, affected primarily by natural events. As settlement in the agricultural period began, forests were cleared and replaced by crops. Poor land use practices and farming techniques resulted in excessive upland erosion and extensive sedimentation, leaving alluvial deposits of up to 6 feet thick on the floodplains. In the 1930s, farms were abandoned and land formerly in row crops reverted to forests. With a general reduction in sediment load during the very recent period, a reworking of stored floodplain sediment has occurred. Downcutting and stream migration has resulted in export of fine sediment, retention of a smaller volume of coarse sediment, and streams have built new floodplains at lower elevations, leaving abandoned floodplains or terraces behind at higher elevations. Terraces may be formed over several periods of alluvial deposition and stream incision. Occurring repeatedly, it's possible to develop any number of terraces. In the present day, terrace remnants may be relatively continuous along a valley or only remain in isolated patches. Generally, when several terraces are present, it may be difficult to distinguish between the lowest terrace and the floodplain. Understanding past land use practices and geomorphic history can be useful in Bankfull identification and help us properly differentiate the floodplain formed under today's hydrologic regime from terraces that were formed under different hydrologic regimes.
We're at Mantua Mill on Western Run in Baltimore County. This is in the Piedmont of the state of Maryland. I'm standing at the left edge of the water, and we flattened the grass here, and the depositional surface of the point bar is gradual, as you can see as I walk up the surface to the edge here of the floodplain, the flat surface that we're defining beyond. The Bankfull stage then would be approximately where I'm standing, as defined by the intersection of the surface of the floodplain. Under ideal circumstances, one might have a similar surface on the opposite side, and the topographic feature defining the floodplain and the intersection with the Bankfull stage is critical in the field. One will have to often, not surprisingly in the field, clear away the vegetation to make sure that you're walking on a surface and not visually misperceiving the elevation of that surface. And as one looks across the stream, you can see the cut bank on the far side. What's evident is that the elevation of the surface of the cut bank is about 1.5 to 2 feet higher, where my colleague is walking, than the height of the floodplain. That surface is in fact a terrace, in the sense that it is an abandoned depositional surface put down by the Western Run at an earlier period of time. The current hydrologic regimen, which involves the combination of water and sediment, is presently depositing the floodplain.
Point bars are sloping surfaces found at the inside of meander bends. The floodplain often forms at the top of point bars as channels migrate laterally across a valley over time. The top of the point bar, therefore, is one of the best indicators of Bankfull stage. Let's see how the top of the point bar corresponds to Bankfull stage in a different setting, at Barber's Creek, a 13-square-mile watershed in the Appalachian Valley and Ridge province of Virginia.
One of the best indicators of Bankfull is the level top of the point bar. As I'm standing here, I am on the sloping surface of the point bar. I'll walk up slope. The slope flattens out, and now I'm standing at Bankfull elevation. At my feet are gravel and sand. As I go up slope beyond this, there's a transition to soil and vegetation. The flow frequency associated with Bankfull at this location was determined using the HECRAS computer model and regional flood frequency regression curves. Based on this information, Bankfull approximates the 1.3-year flood event. Further up the slope, we have a low terrace that corresponds approximately to a 5-year flood interval. It's important to differentiate between the floodplain and the terrace. As I step down here, I'm now standing on the flat upper surface of the point bar that represents Bankfull. Susan to my left is standing on a terrace that's inundated by approximately a 5-year flood event. Remember, Bankfull is the flat depositional surface at the top of the point bar. I'll place 2 flags here to show you where it is. And now walk down the sloping surface on the facet of the point bar to the water's edge to show you the relationship between the water and Bankfull at the top of the point bar.
I'm standing here in Gulf Creek in the Ouachita Mountains of central Arkansas. The Ouachita Mountains, along with the Boston Mountains and the Ozark-Salem Plateau, make up a physiographic region known as the Interior Highlands. The basin area at this point is about 5 square miles. Up here, we can see a very well-expressed floodplain along Gulf Creek. Here we can see clear signs of floodplain development that we can use for identifying the Bankfull stage. In my opinion, the floodplain level is the only consistent indicator that we can confidently use in the interior highlands to identify Bankfull stage. Over here on the other side of the stream, we can see some of the difficulty in using vegetation and cut banks as an indicator of Bankfull flow. Right here we see an example of how moss and lichen or even scour on a rock face is not very helpful or consistent in identifying bankfull elevation. My flag here identifies the level of the floodplain, and you can see that the moss is growing at least 2 to 3 inches below that level. Same goes for the wash line on the rock just upstream. And it's been my experience in general that these indicators are typically not as useful and certainly not as confident as the floodplain elevation. Now, when working in the interior highlands, one has to be careful to not make the mistake of identifying an old relic surface left over from past human activity. Logging in the early part of this century led to numerous access roads being constructed in most of the small valleys in the interior highlands. Here Bill is standing right in front of what is in fact an old relic forest road. And approximately 50 feet beyond Bill, up on a somewhat higher surface, probably a low terrace, Jason is standing. Both of these features are common in many of the streams in the interior highlands, and one has to be careful not to mistake them for the floodplain.
To this point, we've discussed how to identify bankfull stage in a variety of physiographic settings, but primarily at a single location in the channel. However, the best way to identify the elevation of bankfull stage is to use a systematic procedure that involves identifying bankfull stage at a number of locations along a reach of stream channel. Minimum equipment required for this procedure includes a surveyor's rod and level, a measuring tape, and colored flags for marking bankfull elevations. As a first step, refer to any existing data that may be available for a region or specific river. Information including regional curves and gauging station data can be used to approximate the elevation at which you can expect to see the floodplain and its bankfull depositional features in the field. A second step is to select a representative reach of the river in the field where a consistent bankfull elevation can be determined. Begin by doing a reconnaissance of the stream reach. Walk the reach for a distance of at least 20 to 30 channel widths to look for probable bankfull indicators. This distance is generally sufficient to average out variability of pools and riffles and to determine the mean slope of the surveyed reach. Data from regional curves and information about geomorphic history and past land use practices can help you to correctly interpret surfaces and evaluate features with respect to incision or instability. Wade the center of the channel if possible and view bankfull stage along both banks. Visualize the water surface at bankfull and note channel features such as bars, boulders, and root wads that may affect water surface elevation or direct the current. Remember that the key indicator of bankfull stage is the floodplain, a flat depositional surface adjacent to the channel and at the tops of point bars. When you have a general idea of where bankfull stage may be, place pin flags along the reach, but only at those locations where bankfull stage can be readily identified. That is, at locations where good indicators of bankfull exist. This generally means placing flags along the inside of meander bends and along both sides of the channel on straight reaches where the floodplain can be identified. Avoid areas with active bank slumping, including the outside of meander bends, bedrock outcrops, areas with log jams, beaver dams, sections immediately above or below road crossings, and any areas with channel alterations or obstructions that might artificially raise or lower local water stage. The final test of bankfull stage is to make a longitudinal profile by measuring the distance between flags and surveying the elevation at each bankfull indicator with the rod and surveyor's level. While we can't cover all aspects of surveying a longitudinal profile here, the essential data to obtain is a distance and an elevation measurement down the center of the channel at each bankfull stage flag. Specifics of how to do this can be found in the U.S. Forest Service publication Stream Channel Reference Sites, an illustrated guide to field technique, and references such as Dunn and Leopold's book, Water and Environmental Planning, and Luna Leopold's book, A View of the River. This plot shows data from a longitudinal profile of Bankfull stage along a short riffle. Significant scatter of Bankfull elevations is normal. However, the best fit line, drawn through the points, represents the sloping surface of Bankfull flow or the floodplain. The elevation of the best fit line is the best estimator of Bankfull stage at any given location along the profile. Let's look briefly at typical relationships between channel features and the elevation at which they occur. Understanding these relationships can help you evaluate data obtained from a longitudinal profile. An important concept to understand is that as the water rises over Bankfull during a flood, differences in the appearance of the water over pools and riffles tends to disappear, and floodplain deposition occurs. As a result, the slope of the riffles along the channel bed, the water surface, the surface of the floodplain deposited at Bankfull stage, and the surfaces of terraces will all be close to parallel over a distance of about 20 times the channel width. The elevation of your flagged Bankfull stages should be approximately parallel to the elevation of these other features along the longitudinal profile. By plotting data in the field, Bankfull stage identification errors can be noted. Outlying points will be evident and may be rechecked and corrected if necessary. Where your longitudinal profile passes a stream gauge, the gauge height corresponding to the elevation of each channel feature can be determined. Gauge height corresponding to the average elevation of the floodplain is of special interest in confirming identification of Bankfull stage. Information from U.S. Geological Survey stream gauging stations can be especially useful in comparing field-determined Bankfull stage to known stream flows and their flood frequency return periods. To accomplish this, a longitudinal profile in the vicinity of a gauging station is surveyed. Elevations obtained are then compared with the discharges and return intervals from the gauging station's discharge rating curve. As we saw, a channel cross-section plot from Barber's Creek indicated that the field-identified Bankfull stage at the top of a point bar correlates with a 1.3-year return interval, and the low terrace is at the approximate elevation of the 5-year flood. Another cross-section from nearby Craig Creek illustrates similar relationships for a cross-section on a straight channel reach with a flat depositional floodplain surface. Again, the depositional floodplain surface and Bankfull stage correspond with a 1.3-year flow, and the terrace is associated with the 5-year flow. As we've seen, Bankfull stage is typically inundated by flows having return periods of between 1 and 3 years. While there is considerable variability in the recurrence interval of Bankfull flow in different streams, empirical data from the eastern United States indicates that Bankfull stage is typically associated with flood peaks from 1.1 to 1.5-year return intervals. Therefore, if your plot of Bankfull stage is well outside of this general return interval range, you may not have correctly identified the floodplain and Bankfull stage in the field. Data from USGS gauges and other sources has also been used to develop empirical regional channel hydraulic geometry curves. These curves show general relationships between drainage area and a variety of Bankfull channel dimensions, including Bankfull depth, Bankfull width, Bankfull cross-sectional area, and Bankfull discharge in different regions of the country. Since the data are plotted as a function of drainage area, it's possible to estimate average channel dimensions and Bankfull discharge from these curves. The curve for the eastern United States encompasses drainage areas of various sizes and is derived from data compiled in a wide range of geographic regions. Accordingly, there is a high degree of variability associated with these curves, but they can be useful in making rough ballpark estimates of where to begin to look for Bankfull stage in the field. To do so, simply determine the drainage area for a particular river or stream from a map prior to going into the field. Then locate desired channel dimensions on the regional curve corresponding to that drainage area. These general values can then serve as a rough guide of where you might expect to find the floodplain and Bankfull stage in the field. As we've seen, identification of Bankfull elevation may be difficult in the field. This is especially true where the valley bottom is too narrow for an active floodplain, in steep gradient streams that lack a floodplain, and in deeply incised, actively changing channels that lack floodplains due to instability. In all of these cases, there may be no depositional surface identifiable as the floodplain. Another factor confounding Bankfull stage identification in the eastern United States is the preponderance of lush vegetation. Remember that grasses, sedges, and near-stream trees often grow below Bankfull elevation in the eastern United States, and some species, such as willows, always grow below the Bankfull elevation. Other vegetation features, such as the limits of moss growth, lichen lines on rocks, and the lower end of scoured roots, are also poor indicators of Bankfull stage and tend to occur below Bankfull in the eastern United States. Because vegetation frequently obscures sandy depositional surfaces adjacent to streams, try to identify Bankfull stage at times of the year when vegetation is minimal. Sometimes it's advantageous to remove vegetation in order to see Bankfull depositional features, as in this example from the Mississippi River, where grass has been mowed to show the Bankfull surface.
And it shows the flat, sandy surface, depositional surface of the point bar. That is the Bankfull elevation where it flattens off.
Be aware of natural levees in the eastern United States. Levees tend to form along many channels, but natural levees, unlike their man-made engineered counterparts, are not continuous. Thus, channel water will spread onto the floodplain behind the levees through natural breaks. The top of the levee is not the Bankfull surface, even though it is a depositional feature. Bankfull elevation is typically associated with the elevation of the somewhat lower surface behind the levee.
Across from us here is a point bar with a grassy mound, and actually the top of that mound in this wetland system is the top of the hummock. If we look farther back at the brown sand that's deposited in the hollows, that in fact is the elevation of Bankfull. So when you're out in these wetlands, dig down through the grasses and look for that flat hollow bottom that's in between the grassy hummocks, because that is the true Bankfull, where the water first begins to spread out of the channel.
Stream channels are extremely complex, and channel features are formed by a variety of interacting mechanisms. Banks are not always the same height on both sides of the channel due to factors such as bedrock outcrops, colluvial input from hill slopes, bank slumping, or past channel influences that may affect sediment deposition. Braided streams and stream reaches with multiple channels can be particularly vexing. The best strategy in many of these situations is to avoid these complex reaches and look for Bankfull indicators at more favorable sites. Stream channels are continually changing and may be out of equilibrium for a period of time. It's important to be able to understand and recognize factors that disrupt channel equilibrium. Isaacs Creek in the Piedmont of South Carolina provides a good example of a channel that is still working to regain its equilibrium. However, even in these channels, Bankfull features can be identified as they form within an enlarged, incised channel. Finally, wetland streams are important, especially in the lake states, and proper identification of Bankfull stage in these settings requires special consideration.
We're at Sand Creek, northeast of Grand Rapids, Minnesota, in a typical lake state wetland stream. It's an E5 channel, drains approximately 10 square miles. The wetland system may represent as much as 50% of the channels in the lake states. But the floodplain here has a hummock and hollow topography to it. It's quite rough. And so the question becomes, when you're looking for Bankfull elevation, just where in this rough topography is the Bankfull elevation. The key to remembering this is that the floodplain is a point where the energy of flowing water and the energy of flowing sediment spreads out. So when this stream comes up to Bankfull elevation, the water begins to spread at the hollow or the lower elevation rather than the hummock elevation. My left leg is on top of a hummock and my right leg is in the bottom of a hollow. And it's this lower elevation that will accept the spreading water first. That's where the energy spreads, and that's the Bankfull elevation.
As we have demonstrated, finding Bankfull stage in the field can be difficult. In this video, we have concentrated on field identification of Bankfull stage in forested streams of the eastern United States. Identifying Bankfull stage in streams impacted by urbanization or agriculture, while conceptually similar, may be more complex and require different strategies. These impacted streams will differ from those in more natural states of equilibrium in the same region. Be aware that unless some semblance of equilibrium exists, Bankfull channel size is still evolving, and apparent indicators of Bankfull stage are likely invalid. Due to the variety of stream types found in different geographic locations, consistent identification of Bankfull stage requires a rigorous and complex observation process. To assure consistent identification of Bankfull stage, keep the following in mind as you head for the field. The best indicator of Bankfull stage is the relatively flat depositional surface located adjacent to many stream channels. This surface is the stream's floodplain. Recognize the geomorphic context of the channel. Look for terraces and remember that they are the result of previous climatic or hydrologic regimes, often associated with dramatic changes in land use practices. Be especially careful not to confuse the level of the low terrace with that of the floodplain. Recognize that floodplains may not exist along all stream channels. They are most prominent along low gradient, meandering streams. In progressively steeper channels, floodplains may be intermittent on alternate sides of meander bends, or they may be completely absent. Steep, confined streams and streams undergoing rapid change often lack distinguishable floodplains altogether. In these channels, other indicators may serve as surrogates to approximate Bankfull stage. Use them with care, and remember that they need to be confirmed for your local area to verify that the level of these surrogates is the same as that of the primary depositional surface indicator of the floodplain. Likewise, don't be fooled by recent channel disturbance in incised channels. Recently disturbed streams may give false indications of Bankfull. In these channels, the newly building floodplain within the incised channel is the Bankfull stage, not the top of the original stream bank. Employ a systematic approach to Bankfull determination. Identify Bankfull indicators along a longitudinal reach of the stream instead of at a single location. Use the profile of Bankfull elevations from these multiple locations as your guide. Use longitudinal profiles at existing U.S. Geological Survey stream gauges when possible, as this is an excellent way to verify that the surface you've identified is indeed the floodplain and not a terrace or scour feature. As you do this, always keep in mind the basic concept that Bankfull stage and the level of the floodplain are one and the same, and that the best and most consistent identifier of Bankfull stage is the flat depositional surface of the floodplain, a surface formed and reformed immediately adjacent to many forested streams in the eastern United States.